Here we go. Question number 1. What is heat? Use this term in context. Oh, well, let's see if I can minimize this or something. That's most of the code. There you go. 982-4617.
Got it.
And nobody chose the yellow one. All right, so heat is a transfer of thermal energy due to a temperature difference. Right, so put a hot object next to a cold object. There's going to be a transfer of thermal energy from one to the other. That is called heat. No points for anyone. Number 2. What is heat measured in? What's the units for heat? Those do all work. So joules is the base SI unit. What is a calorie? Like that blue one. What is a calorie? So a calorie is the amount of energy that you need to change the temperature of 1 gram of water by 1 degree Celsius. And it turns out that 1 calorie is the same thing as 4.18 joules. Okay, so it does conversion from one to the other. So 1 calorie, same thing as 4.18 joules. Now, you've probably seen calories on nutrition labels, like, oh, this food item has like 500 calories or something. Now on food labels, actually that's a capital C calorie, which turns out to be the same thing as a kilocalorie. So if you say 500 capital C calorie, like food calories, the same thing as 500,000 of these calories that are each 4.18 joules. So look at conversions there, but there you go. There's different ways to quantify energy, and heat is a exchange of energy. Specific heat capacity is related to the amount of internal energy. What? Specific heat capacity. Yeah, needed to change the temperature of 1 gram substance by 1 degree. Yeah, most of you guys remember that. So, do you guys remember last week I was telling you guys that water has a very high specific heat capacity? And what that means is it's really hard to change the temperature of water compared to metals. For example, throw some water in a pot, throw that on the stove. The metal part of the pot heats up really easily. Change temperature, easy to do that. But the water inside takes a long time to change that temperature because water, very high heat capacity. Pour lots and lots of energy in, rarely changes temperature. The reason in the ocean temperature doesn't vary much from one season to the next. Why? Water has a high specific heat capacity. All right, guess all got that. Hey, how about where we are right here, Florida? We're surrounded on 3 sides by ocean water. Have you guys ever been out to the Midwest? Right out to the Plains, Texas, Oklahoma, Nebraska, right? Yeah. I remember I drove across South Dakota once, and it was a really hot day outside. The sun was setting, but it was like 90-something degrees out Fahrenheit. And out of nowhere, this huge storms rolled in, and this huge temperature drop that it's really crazy for someone living in Florida, because Florida, the temperature is pretty stable all year round because we're surrounded by water. But yeah, out in the Midwest, ooh, different story. Oh, the largest extremes in temperature usually experienced where? extremes in temperature. So really hot day, really cold night. That's going to happen. Yeah, middle of a continent. Because those other three options are all near large bodies of water. Ocean, coasts, islands surrounded by lots of water. Temperature is pretty stable because water has a high heat capacity. Yeah, middle of a continent, different story. Surrounded by ocean. On a very cold winter, pipes sometimes burst. Why? There you go. Water expands when freezing. Now, this is the opposite of what most materials do. Most materials, when they change phase from liquid to solid, for example, will occupy less volume, less space, become more dense. But water is the opposite of that. Why? Well, maybe something to do with the fact that water takes a crystal type structure when it turns into a solid. That's why snowflakes have this classic 6 sides. Right? Yeah, so water going from liquid to solid state actually occupies more volume, has less density. That's why ice floats. There you go. It's all embedded in that question. The reason you can hold your fingers beside a candle flame without getting too burnt is why. Yeah, all this would be true. And so the candle flame is going to be radiating away heat energy. So radiation is one type of heat transfer. No, there's probably going to be no conduction. So air is a poor conductor, right? How about convection though? Now there would be a convection curve, but you guys know that hot air wants to rise, right? Because hot air less dense than surrounding air. So there you go. And those convection currents go up. So don't hold your hand right over the flame. So that's not good. But beside the flame, yeah, might be all right. Let's run a quick Paul Hewitt here. I got one lined up. Here we go.
It turns out that air is a good conductor or poor conductor. It turns out it's a poor conductor. And aren't you glad? Because what if air were a very, very good conductor? How would you feel all the time? Begins with a C, ends with O. Put it together, gang. You would feel cold. Let's suppose the air were as good conducting as like a piece of metal. Do you ever stand on a nut at home and lean up against a metal door? Whew, it's cold to the touch. But that metal door has the same temperature as the air around you. So be glad that air is a poor conductor and a good insulator. In fact, when you want to keep yourself warm and you're going to go camp and that sort of thing, don't you get a down-filled sleeping bag? What's all the down for? It's holding air in one place. It keeps the air from circulating. And that down will just hold the. How about animals? You wonder about the animals. How do they make it up in the snow-covered mountains? They're covered with fur. And that fur puffs up and guess what it holds inside? Begins with A, ends with R. Air. And that air is a very, very good insulator. So most of the things that keep you very, very warm in a cold climate like that, which insulates, like styrofoam, yeah, or spun glass, or things like that. They're all what? They're things that hold air. See these thermal underwear they have now? The thermal underwear, you look at the thermal underwear and all this is like a net, like a fish net, and you put that on, and that's going to keep you warm. But over that fishnet underwear, put a regular t-shirt. And now what's trapped between your skin and that t-shirt? Begins with an A. All right, ends with R. Air, okay? And can that air circulate? If the air warmed up and just went away, then you get cold again. But it's all held there by the little knitting. That's what it is. When that stuff first came out, I looked at that and said, what? Because, this is going to keep you warm, honey. And they show you something with all these holes. You say, oh, these holes, that doesn't sound right. But wait a minute. I know what that is. It begins with a P. It begins with an F. What is it? Oh, you don't be knowing. Physics.
Yeah, physics. Heat travels to the sun from the sun to Earth. Radiation, electromagnetic radiation. There you go. It couldn't be conduction because there's no direct contact. Couldn't be convection. It's a giant vacuum of space. Radiation. Ish. The reason light colored clothes help keep you cool in warm weather is because reflect a lot of energy. There you go. So light colors reflect a lot of energy. Dark colors absorb energy. Which cools at a faster rate? Ooh, a little tricky question here. A pot of boiling water or lukewarm water? Which would change its temperature at a faster rate? Ooh, 44. Now, why would boiling water cool down more quickly than something close to room temperature? Let's switch the screen over here. Not share. I'm gonna draw you guys some picture. So this is related to something called Newton's law of cooling. So, well, I'll give you a picture, a formula, and a graph. Start with a picture. Let's do a pair of pictures. So you got a cup, like a styrofoam cup full of water, and got a thermometer stuck in here. I'm watching the temperature as a function of time. And we're watching that temperature go down, right? Now, what's the rate change of that temperature, or actually how I'm going to capture for Newton's law of cooling is what's the rate change of heat energy, say like leaving that hot cup of water? Well, it goes like this: rate change of heat energy. This is kind of a calculus type notation. So change in heat energy is per unit time is equal to gonna have here. This formula right here. Right. So what is each of these variables? So H refers to a heat transfer coefficient. Let's say like if I have a cup of water versus a cup of olive oil, you think they probably cool down at different rates? Probably so. And that's sort of embedded in this H, kind of like a material property. This A refers to the area of contact. So remember saying this is like a styrofoam cup. What if instead of that styrofoam cup, I had a styrofoam pan of the exact same amount of water? Right, so this volume of water, this volume of water are the same. Let's say they start at the same temperature. I have a thermometer stuck in this guy too. Thermometer. Oh, hey guys, what do you think would cool off faster? Everybody look up here. What's gonna cool off faster? What's gonna cool off faster? This cup of water or this pan of water? Show of hands. How many guys say the cup's gonna cool off faster? Who says the pan is gonna cool off faster? Okay, most of you guys say this one, right? And you're right, because let's say that if this pan has like twice the surface area contact with the surrounding environment, shouldn't it cool off at like twice as fast, like twice the rate? Okay, and then the third thing you multiply in, so we got this material property, heat transfer coefficient, we got the surface area contact. It is the difference in temperature between that mass and the environmental temperature. Okay, here's where the graph is going to come in. So if you do temperature as a function of time, okay, and say you start off hot, cup of water, some high temperature, and let's say the environmental temperature, like room temperature, is like down here. Okay. If I asked you guys to fill in that graph, do you think you guys could apply some critical thinking and draw that graph? Huh. How about this? There's got to be a point here. So at time 0, hot water, right? It's probably going to come down over time, right? And if you waited like a whole day, do you think eventually this water would reach room temperature? Right. That's to say, do you think there's probably some version of like a horizontal asymptote at the environmental temperature? What does the rest of that graph look like, do you think? You guys think it probably looks something kind of like that. That look pretty reasonable, something like that, right? And now here's where this is going to tie back to that Kahoot question, because Newton's law of cooling. I wanted to go over this with you guys. I just don't have a textbook type question for you. As if you hold your either like a pen or a pencil or a ruler like flush to the graph, you guys see how it starts off with a really steep slope, and then right here it's kind of a shallower type slope, and then as it approaches room temperature, environmental temperature, that slope approaches zero. You guys see that? Right. What I just did with you guys is the slope of a tangent line, instantaneous rate change. That is a calculus concept. I bet a couple of you guys are in calculus and probably familiar with doing something like that. Okay. Do you guys see how if the gap in temperature between the object and the environment is very large, there's a really fast rate change of temperature, but then that slows down over time? Okay. And then that sort of lines with us, like a rate of energy exchange, similar idea. Right. Happens fast at first and then slows down as those temperatures reach equilibrium. Oh, Newton's law of cooling. Hey, that's it right there. Says that the cooling rate depends on what? Yeah. Okay. So temperature difference between object and surroundings. That's this bit right here. Right. Now there are two other answers that would have been good. You could have said the surface area that's exposed between two surfaces. You also could have said H, the heat transfer coefficient, which just were not options. There you go. Those are all factors. A cup of hot coffee will cool faster if it what? Cool faster. There you go. You guys think the cream might be like insulation? Nice, something like that. Yep. Planet Earth loses heat primarily by what? Ooh, no winners. So the temperature of the Earth is relatively stable. I mean, you guys know in the last few decades it's ticked up a couple of degrees, but for large geologic time periods, see, there's an import of energy and there's an export of energy, and somehow those are pretty close to being in balance, right? Now, where does the Earth get its energy from? And I'm thinking of two sources. The sun, that's one of the main sources. And guys, what's the other main source of where Earth's thermal energy comes from? Huh? The core. Yeah, geothermal. There you go. That's the two sources, the sun and geothermal. So if Earth is importing all this energy continuously, then how's the temperature stable? Well, because it's also radiating away heat energy too, right? And that's approximately balanced. Now, it can't be conduction because the Earth is not directly touching anything, it's surrounded by a vacuum of space. And well, same problem with convection. Now, maybe a tiny amount, possibly by convection, because solar wind is always picking off the top parts of Earth's atmosphere a little bit at a time. So maybe a tiny bit of convection, but yeah, mostly radiation. Go. Condensation occurs when matter changes from a what to a what? Condensation. See some dew on the grass. Have a glass of cold iced tea, and then it gets all watery on the outside. Yeah, gas to a liquid. The humidity in the air condensates, forms a liquid. Clouds form when warm air Yeah. Actually, that's a sequential process. So the warm air rises, expands, chills, condensates, forms cloud. There you go. In that order. Rises, expands, and chills.
Thank you.
Clouds.
No problem.
When water freezes. Is that exothermic or endothermic? Water freezes. Yeah, that is an exothermic process. I mean, for something to go from a liquid to a solid, it's losing internal heat energy, right? It's getting colder. It's giving away energy. That doesn't quite make sense. What if you turn that around? What if you said when snow melts and goes back into liquid water? Wouldn't that be a process that would take energy? It should be opposite of this. Okay. All right. So similar question coming up pretty soon to that too. Let's follow that. As atmospheric pressure increases, the boiling temperature of a liquid what? Also increases. Remind you guys remember this right here? So, where are we on this pressure and temperature diagram? Well, we're at 1 Earth atmosphere, so that's this red line skirting across here, 101,000 pascals. And room temperature is about 25 degrees Celsius. That puts us right about here. So how do you boil water? Well, you might say put it on a stove, go to the right here, boil right there. But remember, there's another way to boil water too, which is if you decrease the pressure, you can cause reduced pressure boiling, right? Or you could do a combination of the two. If you go up to Denver, Colorado in the mountains, a mile high, then the required boiling temperature is not as much. It might be somewhere closer to like 97 degrees Celsius, right? But the question was framed in the opposite way. So what if you have, say, a pressure cooker? You guys know a pressure cooker? You can increase the pressure of more than 1 atmosphere, and that will allow you to heat up water more than 100 degrees Celsius, and it'll stay liquid. So that's like right up here. Yeah, there you go. When snow forms, air becomes warmer because. Yeah, changing from a vapor to a solid, a process that gives off energy. Right? That's that exothermic process that we were just talking about. Okay? So change phase to something colder, you give away heat energy to do that. The surrounding environment warms up a little bit. If you want to cook boiled eggs in the mountains where the air is really thin, your water boils at 95 degrees Celsius, way up there. What should you do? Oh, good call. Must have got that. Boil eggs for a long time. See, no, nobody did pick the red one in this class, which is awesome. But well, why would that not be a good answer? Well, say you turn the flame up somewhere and the water starts boiling at 95 degrees Celsius. So you're way, way up in the mountains. 95 degrees Celsius starts boiling. Said, okay, well, this water isn't hot enough and I want to cook the egg faster. So then you turn up the flame more. Is that right? Well, that didn't really help you because the water temperature flatlines. You guys see that this poster hanging right here, where you're changing phase from liquid to a gas, will stay at the same temperature. Yeah, so you just have to boil the eggs for a longer time. That's how it is done. The lowest possible temperature in nature. All right. There are two good answers up there. 0 Kelvin, because that's absolute zero. But in Celsius, that's negative 273.15 degrees Celsius. So that works also. Do you guys remember these temperature scales right here? Now, I should say too, I just noticed earlier today that these are not to scale, so that they don't correlate linearly, but you get the idea. So different temperature scales. Okay, so 0 Kelvin down here correlates to negative 273 degrees Celsius, or also negative 416 degrees almost Fahrenheit. Okay. Hey, how about this? There might be some questions coming up pretty soon that involve like scaling temperature by some factor, like doubling or tripling a temperature. Now, if that's the case, hey guys, what is if say you had something at 10 degrees Celsius, that'd be pretty cold, right? 10 degrees Celsius. What if you double that temperature? Would that be 20 degrees Celsius? How about no? Because 10 degrees Celsius, remember, Celsius is a relative scale. So the number 0, it just happens to be a random point where water happens to change phase. So you can't do 10 times 2 because that's not really doubling anything. What you would have to do is convert to Kelvin, which is an absolute scale, double that number. And then if you want to convert back to Celsius after that, you could do that. So the process would look more like this. 10 degrees Celsius, that's the same thing as 283 Kelvin. That times 2 is like 560 something Kelvin, like way above the top of the scale. And then convert back to Celsius by subtracting 273. Okay, so that is how that would work. There's a similar type question come up. Somewhere here soon about that. Oh, this is it. This is it. A volume of air at 0 degrees Celsius. What if you double the temperature? What is 0 degrees Celsius? Then you double the temperature. Now what temperature are you at? Okay, most of you guys were listening to me. Get that 0 degrees Celsius, same thing as 273 Kelvin. You double that, you get to, what would that be, 546 Kelvin, I think. And if you translate back to Celsius, now you're back to 273 degrees Celsius. Okay, let me flash this temperature scale up here again, which again is not exactly the scale, but better than nothing. So if you're at 0 degrees Celsius, you already have all of this internal temperature, right? You already have 273 degrees ready to go. If you double that, well, now you're way up around, positive 273 degrees Celsius. Yeah. The first law of thermo is a restatement of what? Yeah, conservation of energy. You can't create or destroy energy. You can only transfer it from one form to another. There you go. First law of thermo. Adiabatic processes, which processes that involve no mass or heat exchange with surroundings, occur in. Where do you think some good approximations of these adiabatic processes happen? Yeah, all the above. Yeah, both those would happen. Could be approximately closed systems, some kind of thermodynamic process going on. The greater the difference in temperature between input and output reservoir for a heat engine. Ooh. Yeah. All right. Yeah, the greater the efficiency. Give you guys a couple examples on this one. So, where is Bill? Oh, Bill Nye. It's Bill Nye time. That's why he's here. So, you guys remember Bill Nye's Stirling engine? So, he has a beaker of very hot water here. And oh, gets that thing a push in. Look, it's rotating clockwise. wait, where's this mechanical energy coming from? Well, it's coming from, there's a transfer of thermal energy from this hot water into the surrounding room because the hot water is considered the hot sink, that's the term for that. And the room temperature room is considered to be the cold sink because it's relatively colder. There's an energy transfer, goes through the Stirling engine, and part of that is going to convert to mechanical energy. Then later on here, zoom ahead a bit, puts it on the cold beaker water, the ice water, and it reverses direction. Remember, it goes counterclockwise? Because now the direction of heat flow is from the room into the beaker water, right? It's reverse direction. The hot sink is now the room, and the cold sink is that beaker of ice water. Right. Now, there's some percentage of that heat exchange that goes into mechanical work, and that's involved in the efficiency of that process. So I have an equation for you guys. Switch screen over. I'm gonna do an equation. Stop sharing. All right, back over here. So there is an equation for efficiency for something like that Stirling engine. It goes like this. Efficiency, that's Greek letter eta, that stands for efficiency. Well, at least in this context it does. Might use it for other things, other places. Equals 1 minus the temperature of the cold sink divided by the temperature of the hot sink. Okay. Or you could rewrite this as temperature hot minus cold all divided by hot. You can do that too. Okay. So let's run an example. Remember Bill Nye's Stirling engine there? Or got one too. It's just across the room here. So let's say the cold sink was like at 0 degrees Celsius because it was ice water, right? 0 degrees Celsius. And let's say the room was like 25 degrees Celsius. Can anybody tell me what the efficiency of that would be? This is kind of a trick question here. All right, so let me say those numbers again. Let's say that the cold sink was this ice water. Let's put that at 0 degrees Celsius because that'd be a reasonable assumption. I'll say that the room was a nice cozy 25 degrees Celsius. Probably pretty close to what it is in this room. Okay. What would the efficiency? Well, but you could do 0 divided by something, right? Right. Now, if you plug those numbers directly, here's where this might be kind of a trick, maybe. What is 0 over 25? Is that 0? And 1 minus 0, is that 1? And 1, would that represent 100%? Like, if you got 1 exactly, that's like 100% efficiency. Would that machine be 100% efficient then? Good call. No, because I've been tricking you guys the whole time. Guys, can you put in Celsius values into these? You have to put in Kelvin. Because if you're taking ratios of temperatures, you better be using an absolute scale, right? See if you're using a relative scale, you might get like, oh, what if it was like negative 10 degrees Celsius? So you get something over 100% efficient, which doesn't make any sense, right? That would ruin the first law of thermodynamics. So this is how you X this up, right? 1 minus, and then for 0 degrees Celsius, that's 273 Kelvin divided by 273 Kelvin plus the 25, the extra 20, right? All right. I'm looking at this number right here, 0.08. Okay, guys, 0.08. That means it's what percent efficient? 8%, right? Because go from a number to a percentage, you just multiply by 100. Right? Yeah, that is 8% efficient. There you go, which is probably pretty close to what he had going in on that video. So I bet that Stirling engine was about 8% efficient for that particular environment. Say like 8% of the thermal energy was converted to mechanical work. Oh, I was gonna ask you guys another question. I'm gonna switch back. I think we got time. All right. If you did want to achieve 100% efficiency, maybe there's one way to do it. That's to do what? What's the only way to get to 100% efficiency? The cold sink would have to be at what temperature? Absolute zero. That's the only way. Absolute zero, right? Because absolute zero divided by anything would be 0. 1 minus 0 is 1. That'd be 100% efficient. Okay. But that is never going to happen. So machines will always be less than 100% efficient. Kind of makes sense, right? Next question. Two identical blocks of iron, one at 10 degrees Celsius, the other at 20 degrees Celsius, put into contact. Let's say the colder one cools down even more to 5 degrees and the warm one warms up even more to 25 degrees. Now, that's never going to happen because that would be a violation of what? Ooh, got two winners. So actually, in terms of the first law of thermodynamics, that conservation of energy, it checks out, and actually everything's perfectly fine. To get, they said identical blocks, let's say like the same mass, the same material. If one loses 5 degrees Celsius and the other picks up 5 degrees Celsius, right, equal temperature changes, then in terms of the quantity of energy going around, everything's conserved and it's perfectly fine. But you guys remember that second law of thermodynamics, the one that gets real abstract real fast that involves entropy, right? That has something to do with the arrow of time, tells you the time directions of these things. So if you put a warm object next to a cold object, why doesn't the warm object heat up more and the cold object cool down more? Well, that would be a violation of second law of thermodynamics, because that would be a decrease in entropy, and that can't happen. Okay? There you go. That's the only violation going on. Okay. Now you could have the reverse, right? Objects put next to each other will tend towards equilibrium temperature. Okay. So the cold one wants to warm up a little bit, and the hot one wants to cool down a bit. 26, refrigerator. You go home, open your fridge door, leave it running all day. What's going to happen to your house? Yeah, I'll have a hot house because you have cold air dumping out the front of the fridge, but don't forget the hot air dumping out the back. Remember, refrigeration, air conditioning, same technology. That is an energy intensive process. I mean, it's really hard to cool down air. Easy to warm up air, you just light a fire, but how do you cool down air? That's kind of tricky. That's an energy intensive process. And to like vastly oversimplify this, the amount of hot coming out the back of the fridge is going to outweigh the amount of cold coming out the front. So when you mix all the air back together, overall, it's going to warm up the house a little bit. I mean, that's the reason the fridge is plugged into the wall, right? It's importing energy off the grid. Might be an indication that the temperature of the room is going to go up. What is the ideal efficiency for a heat engine operating between those two temperatures? Oh, we just ran a calculation like this. Ooh. It's the efficiency. Oh, one winner. One. There's one. Over and show you guys this. Ooh, got it. Right. So you guys remember this formula from a few minutes ago? Right, the efficiency is, say, 1 minus the ratio of the temperatures for your sink, cold sink over hot sink. Okay. Now, you have to plug in numbers in Kelvin, right? Can't use a relative scale. Now, very conveniently, those numbers were in Kelvin, so you can just plug everything directly, right? They told you the cold sink was 310 Kelvin. That's pretty warm, but we'll go with that. And the hot sink was over 2000 Kelvin. Right? Okay, so we got some kind of industrial machine going on. So if you run this equation, see 1 minus 310 on 2050, you get 0.8488. Oh, isn't that like 0.85? Isn't that like 85%? That's 85% efficient. Say, as the heat is moving from the hot sink to the cold sink, 85% of that energy is able to be turned into mechanical work. Back up to Screw-Doo. Up to the podium with the bronze, the Donald, the duck, the silver, Cheyenne duck, the whole duck family, and the gold, Caden. Runners up, my big something and Levi. All right, nice job, guys. All right. We got a few minutes left here, so let's do this. Oh, tomorrow I'll solve some more of these problems with you guys. So let's see where we are in the context of this class. There was this page I gave you guys quite a while back. It says chapter 12 thermodynamics on one side. Now we solved all these problems already. And then we're moving on to this side. It says chapter 13 and list a bunch of topics. We got ideal gas law, Archimedes principle, Pascal principle, Bernoulli principle, thermal expansion. Take a quick glance at these questions and see what principles would align with which type question. Now, the first two questions I see, cylinder or piston, gas, maybe weights. That's making me think maybe something to do with ideal gas law. Now, ideal gas law, remember, is a composite of three smaller laws that led up to it. There's, what is it, Charles' law, Gay-Lussac law, and Boyle's law. So you might be able to pick one of those laws individually for each one of these 10 questions, depending on whether you're pressure and temperature or volume and pressure, right? So some combination. But ideal gas law will just handle everything. Right? So we can just apply that. Number 84, antique statuette of a bird suspended from a spring scale, reaches this many newtons, then suspended in the water and force rating goes down. What material is the statuette made of? Hey, this is what we did back on Friday. You guys remember the no internet day? No, I'm still going to upload a video. I just have to put that together, recap what we did back on Friday. Let's look real fast. You guys remember I was asking what is the density of this material? You guys remember that? And I gave you, well, obviously the object. I gave you guys a spring scale and a beaker of water. That's what I gave you. I've got the notes right here, what we did back on Friday. Let's look at that real fast. Now, density, you could do mass per unit volume. So you could dunk in the water, look at the volume change, take the mass, divide by that. That'd be perfectly fine. Or there's a real tricky physics way to get it too, which is set up this free body diagram, say here it is submerged, here's the weight, here's the buoyant force, here's the smaller spring scale force now. And then you can say, here's Archimedes principle, here's buoyant force in terms of the free body diagram, do some crazy switcheroo, and eventually get the density of that material only in terms of the spring forces and the knowledge of the density of water. So that's a way, yeah. That's pretty much what that question is asking, is what we did back on Friday. Number 87. What is the apparent weight of a rock submerged in water? That sounds like a Archimedes principle type question, right? Also very similar to the free body diagram we were just looking at. So some version of that. Number 90. Here's the density of salt water and ice. What percentage of the volume of a floating iceberg is submerged? I think I ran a PowerPoint where I set up the free body diagram. That would be the first step to answering a question like this, right? There's two forces on an iceberg. Its weight pulls it down, a buoyant force holds it up, put those in balance, apply Archimedes principle, and then you can figure out the percent volume that is submerged. I'll take you guys through that. How much longer will a steel bridge be when the temperature changes? That sounds like thermal expansion. What's the percentage change in the volume of a concrete block with the temperature change? That sounds like thermal expansion in 3 dimensions, right? Volume change. This one's length change. This is volume change. Hydraulic lift. That looks like Pascal's principle. Water flowing through a pipe with changing diameter. That looks like Bernoulli principle. And then what's the pressure changes inside the pipe? Yep. It's all Bernoulli right there. All right. I think we got conservation of flow followed by Bernoulli. All right, so that is a snapshot of what's coming up later this week. So let's call that a pause point right there. Yeah.